Hi, I'm Hank. In this tutorial, I'm going to go over the derivation and usage of three functions I like to call superfunctions just because of how powerful and versatile they are. So the first function is going to allow you to get points in 3D spherical coordinates and translate it back into Minecraft's 3D Cartesian coordinates. It can allow you to do stuff like this. Okay, that's the first one. So the second one is going to allow you to get the rotation vector between two entities, which can allow you to determine things like this, whether or not an NPC is looking at you or not. Right now, you say he says I can see you. If I go back here, he can't see me anymore. He still can't see me. I go around here again, he can see me. If I'm close to him, you can use this function to manage the direction of knockback. So no matter what direction he's facing, no matter what direction I'm facing, it's always knocking me away from the NPC. And you can also use it to determine if you're blocking. So right now it says you're facing me and blocking. If I look away, it's just going to knock me back. You can do it either way. So you can use this to make a check for if a player is shielding or not. So that's what that can do. And the third one is used to draw lines with particles. You can either have the lines show up instantaneously or you can draw them out with various time delays. So those are the three functions I'm going to be going over. Let's start with the 3D spherical to Cartesian one. So the general idea with this one, let me see over on image here. These are the two different coordinate planes. So you have the blue representing a vector in 3D spherical coordinates, and then you have XYZ here representing the same vector in 3D Cartesian coordinates. What we want to do is we want to be able to give a distance, which is going to be r here, a rotation represented by theta, and a pitch represented by phi here, and then get this point, but the xyz components of it. So you might already know this, but Minecraft does have rotation axes. When you set the rotation type of the NPC to manual, you get these rotations here. So he was at 0. If we set it to 90, he'll face along 90. So these are the rotations in the Minecraft game world. There's 0, there's 90, there's 180, 270, and then 360 just goes back down to 0. And then 0 points along the negative z axis. So that's negative z, that's positive z, that's negative x, that's positive x. So set this back to 0. Okay, so let's just start with trying to get a point somewhere around here. So we have an angle. It's going to be the angle between 0 here and wherever the point we want to be. Okay, so let's define our angle. Let's just start with 45, something like that. So let's start with just the two-dimensional plane, not worrying about the height, just the two-dimensional from here to here. How do we get those different components? If we use this angle to make a triangle, so this angle makes a triangle, one leg of the triangle goes here, one leg goes to where I'm standing, and then one leg goes back to the NPC. So these two legs here, these are the z components and the x components of the triangle. The angle is between here and this, I guess, vector between the NPC and me, and then that triangle has two legs, has a leg here in the z direction, and has a leg here in the x direction. We can get the size of those two legs by using the angle and sine and cosine. So what those are going to be are they're going to be the sine and the cosine of the angle respectively. Now, if we try and test it out now, right now I have the NPC set up to spawn a particle. We're just going to make it so that this dx and this dz are added to our current x and z values. If we try and do it now, particle shows up over there. That's not right because the angle we gave was 45. The reason for this is Minecraft's axes are flipped. If you're looking at it from a mathematical standpoint, you do need to throw an extra negative in here. So we'll throw that negative in right there. Now, when we tell to spawn the particle, it's going to spawn it here. Actually, that doesn't quite look like 45 degrees. Let's test something else. Let's try 20. What's this going to give us? 20 is also giving us that number. So why that is we forgot to convert this to radians. So this is degrees, sine and cosine here, they want radians. So math.pi divided by 180x. This is going to convert it to radians. So now here we have it at 20 degrees. And then if we change this angle to 45, we have the point here at 45 degrees. Now if we want, we can scale this distance. If we add a distance parameter, now whatever the distance is, it's going to get the point, and that's going to multiply these scaled dx and dz so that the point spawns farther away. So distance of 2, point's further now. If we change it to 3, it's going to spawn even further. We can play around with these to get any point we want, so let's do 300 and 1. So 300 should be like around here. And there it is. Next, we want to get the y component of this, the height portion. In order to get the height portion, we're going to need the pitch. So this was the rotation, just going around in circles. Now we're going to need the pitch, looking up and down. Let's make that value here. Okay, so now we have 45 degrees pitch. Now how do we get the y component off of the pitch? Well, it's just going to be sine of the pitch. Now we've already done something wrong. What is it? We don't have it in radians. There we go. Now this dy is going to be sine of the pitch. So if we add the dy to our y value for spawning the particle here, it should show up a little bit higher now. Now this isn't exactly correct for getting us points on a circle using spherical coordinates. The reasoning being is if we have a circle here, say this is just a cross section look at the NPC sideways, and then this is our rotation line, and then this is our pitch line here. Okay, so we just spawned a particle up here. We spawned a particle here. Now, if we look down here, the distance on our xz plane, it's been shortened. So this is the distance that we specified, but there's this component right here that it's been shortened by. But how do we get this component to reduce the distance? Well, the height we had here as sine of the pitch, right? But cosine of the pitch is going to give us this portion down here. And as this angle gets smaller, the cosine of the pitch is going to approach 1. And as this angle gets bigger, say the particle's up here, as the angle gets bigger, the value provided by cosine is going to get closer and closer to 0. So all we have to do is scale our distance factor by the cosine of the pitch. So let's do that here, distance times cosine of the pitch. Cosine of the pitch. It doesn't look like much here, but if we were to take this distance scalar away and then try to have this spawn at a pitch of 90, right? So the pitch of 90 should just have the NPC looking straight up, right? Or the particle should spawn straight up. Let's actually change the distance so that you can actually see it and it's not inside the NPC's head. So it should be spawning straight up, but it's not. It's spawning out here 3 blocks and then up 90 degrees. We need to scale down the distance using this cosine factor in order to actually get the particle to spawn above him. We forgot to vary the distance of the height factor here. So if we add the distance factor in there, now it spawns 3 blocks above. So now using these, we can get any point around the NPC in a circle using a angle rotation, a pitch looking up or down, and then a distance. Now we have this math. Now the next step is going to be we're going to turn it into a function. We'll use dr for the angle here. We'll use dp for the pitch, and then we'll just use distance for the distance. When we do all this math, we end up with 3 components. When we make a function, we're going to want it to give us these 3 components back, so let's set up a return statement. So we're going to have this function return us an array that has these 3 components that we want, right? Let's move the math now. And now because we've named our function inputs, we need to change the names here as well. So change the name of the angle, change the name of the pitch. And the name of distance stayed the same, so we're fine. So if we give this front vectors function an angle, a pitch, and a distance, it should return an array with the 3 x, y, and z components needed to reach that point. So let's set that up here. So our dr here is the angle. Okay, so now, but up here in the interact function, we don't have dx, dy, dz anymore because they're returned by this function. Instead, we have deltas. So deltas is an array. The first component here is dx. So if we want that delta 0, that's going to get us dx, and then likewise delta's 1, delta's 2. So the first index, which is 0, dx, second index, which is 1, dy, third index, which is 2, dz. So this should do exactly the same thing that we had earlier, except now we have a function to do all the math for us, and then we can call this wherever we want in different functions. Yep, spawn to the same spot. If we change our angles here, say we want the angle to be, let's do 90 degrees, and then the pitch to be 45 again, distance be 3, so it should be over here-ish. Okay, there it is, 45 degrees. If we lowered the pitch 0 degrees, it should just be level with the NPC or out here. Yep, and there we go. Now, what if we wanted these rotation pitches to respect which way the entity is looking? So for example, what if we had the entity looking along the 90, right? And what if we wanted to spawn whatever we wanted to spawn off to the NPC's right, right? Well, if we added the rotation of the NPC into our angle consideration, we can do that. So we're just going to do that in our function down here. Let's make a new angle and pitch variable. And then let's replace what's being used in the functions here. Now we'll reassign these so it's set up to function pretty much the same how it is. We're just adding an intermediate variable so we can do additional calculations on dr and dp here. If we want to add the entity rotation, we should pass in the NPC as one of the fields here. So let's add an entity field to our front vectors function. Now if we want the angle to be relative to where the NPC is facing, it should be the NPC's angle, which is 90, plus whatever angle we want. So whatever angle we pass is the angle we want, should be plus the entity's rotation. There we have it. Now there's one more thing we're missing. dr here is in radians, but entity get rotation is not. So what we're going to do is we're just going to move this down here. And we're going to do that after they've been added up. We'll do this to pitch as well. There we go. And then let's add entity get pitch as well here. So there we go. So now this should spawn the particle with respect to the NPC. So it should spawn at 90, not on 90 here, but 90 from the viewpoint of the NPC. And there we go. It spawns on the NPC's right. You can see as he turns, the location that the particle is spawned at also turns. Now what if we did this with pitch as well? So let's do 90 out and let's do 45 up. Let's do distance of 2. It's not moving. Why is it moving? Pitch, pitch, entity get pitch. Right? And our conversion. Let's try 90. Let's see if that does it. Still doesn't move. Did I do something wrong? We doubled down on our conversion here. So now, there we go, it spawns up there. So right now this seems fine, this pitch rotation. That's because the entity's pitch is 0, because he just keeps looking on the horizon. There's something weird with Minecraft's pitch. I have a script that I'm here to show you, where it's going to message me our pitch as the player. As if we're looking on the horizontal, it should be close to 0, which it is, it's pretty close to 0. If we look up though, it increases negative. If we look down, it decreases positive. So if we look up, we want it to be 90, but it's negative 90. If we look down, we want it to be negative 90, but it's 90. So we can just fix that by throwing in a negative here. So now as we look up, it goes to positive 90. As we look down, it goes to negative 90. I don't know why Minecraft inverts the pitch. That's just the way it is. So to fix that here, we just add a negative to the entity pitch right here. So there we have that. Here's our function to get a point relative to an NPC wherever we want. See, as he turns, the point changes. If we have him look up by jumping, it also changes. It goes a little bit higher because it adds 45 to his current pitch. So it's going to go a little bit higher. Now, what if we didn't want that though? What if we wanted the particle to always spawn in the world's frame? So at 0 here. Well, we could just make an option in the function to do that. So we'll just have two different ways of determining the angle and pitch. We have two modes here. Let's add mode as a parameter. In the first mode, we'll do it in the world-centric frame. So move angle and pitch to each of these. In the world-centric frame, we only want to give it the angle that we specify in the function inputs. Same with the pitch. There we go. World-centric frame, just dr and dp. Then entity-centric frame, we add the entity's rotation and pitch to dr and dp. So now up here, we need to add that parameter here. So 0 here should be in the world-centric frame. So if we have the angle be 0, pitch be 45, it should spawn up here regardless of where the NPC is facing. So as you can see, it moves around. It might not be immediately obvious why something like this is useful, but in certain situations it will come up where it's like, oh man, I wish I could just have it pointing in a specific direction that I set. And with this, you'll be able to do that. Here it is. This is our completed function. Now let's do something with it. Let's try and spawn a sphere. How we're going to do that is we're going to make two different for loops. In order to get, the points of a sphere, we need to cover all the rotation points. That's going to be 0 to 360, right? All the rotation, 0 to 360. And then for pitch, we need to cover negative 90 to 90. So let's set up two for loops with those two limits in mind. There we go. We have two loop variables here. We have I, which will represent our incremented rotation going from 0 to 360, and j representing our incremented pitch going from -90 to 90. So now we'll just set up a front vectors call with each of those rotations and pitches. And the distance we can just keep constant. Now, something to keep in mind is this is a nested loop. This first loop is going to run 360 times, and the second loop is going to run 180 times. If you multiply those two together, it's going to be like, I don't know, 50,000, 60,000 times. That's a little too much. What we're going to do is we're going to compress this, how many times it runs. So instead, we're going to have this first loop run 36 times, and the second loop run 18 times, and then we'll just compensate by increasing our loop variables here. So this will give us the points we want. Let's just initialize that to a array again. Let's move the spawns in here. We have a for loop set up that's going to go cover all the points we need for a sphere. And then each of those points, or the deltas needed to reach those points, are going to be added to the NPC's coordinates to get the locations on the sphere. And there we go, we have a whole sphere. All right, so that's the front vectors function. Let's remove all this stuff for now. Let's just move this function down. We'll pull it back up later. Okay, next one we're going to try to do is trying to get the rotation vector that will point from where he is to where I am. A better visualization on what that's going to try to do is if I'm standing here relative to the NPC, we're going to want the function to spit out 270 because that's where I am in the world's rotation reference frame. Here we want to spit out 180, here we want to spit out 90, and so on. So essentially what we're going to do is the opposite of what we did previously. Instead, where we took an angle and got the components, this time we're going to take the components, which we can measure using ours and the NPC's coordinates, and we're going to get the angle by using the inverse tangent with trigonometry. The difference between our two coordinates gives us the two components, so final minus initial, final minus initial. Now, we have to remember, because Minecraft has its inverted coordinates thing, we have to flip the sign here of this mathematical operation here. Now that we have that, we can get the angle. The reason we do d dx over dz here is if we check the angle, right? So here's the z component, here's the x component, tangent, which is the angle between this here and the hypotenuse of the triangle I'm trying to visualize here. It's going to be the opposite, which is the x component over the hypotenuse, which is the z component here. Tangent here. And then we have to remember that this is going to return radians, so we need to convert that to degrees. Let's have the NPC say the angle now. Now let's check if this is right. So we're close to 0, so it should be like something between 0 and 10. There we go. 10. All right, it's actually kind of big. Let's make it round this. Okay, there we go. 545. Okay, so we see it works for now, but once we cross this 90 degrees here, it's negative. And then once we cross back over here, it's positive again, and it's like not even cool, like negative, like it's not right. So what we have to do to fix this is we need to split it up into two cases. The first case we're going to look at is when dz is positive, so when we're on this side of the green line. And the second case we're going to look at is when dz is negative, so we're on this side of the green line. Let's set those two cases up now. Okay, so here are two cases, if dz is greater than or equal to 0 and if dz is less than 0. For the first case, with dz greater than 0, which is we're on this half of the line, everything is fine when we're 0 to 90, right? So you're getting close to 90, 89, yeah, that's about right. And then over here, get close to 0, right? But once we cross over here, once we're negative, things aren't correct anymore. But these are small negative angles, right? So this negative 30 that I'm at now, it's the same as if I were to go to the NPC rotation here, and set him to 330, right? Because 330 plus 30 is 360, right? So he's facing the same direction. Small negative angles are the same as large positive angles. So I'll set it back to 0 real quick. So small negative angles are the same as large positive angles. What we can do is take advantage of that to convert these negatives into positive by just adding 360 to them. The angle is less than 0. Angle is itself plus 360. So this is still our first case, so now let's test and see if they work. Okay, it still works when we're on the 0 to 90, but if we cross over here, it should be like the high 300s. There we go, 300s, go down all the way to 270, and it works just fine. Okay, now we have over here. Over here is not right. This is our dz is less than 0 case. We're going to start off by just flipping the sign of dz. Now, okay, angles are positive now still, but now they're still negative. So if you look at these long enough, and this is what happened when I first did this, I just realized like, wait, there's just one number I added them all because they're still consistent, right? Because here we're close to 0, then here we go to 90, and then here we go to negative 90, right? So all we need to do is add one number to that, and we'll get the right numbers we need. And that number is 180. So 180 minus this, we'll be fine. Now just to verify, go all the way around. Okay, so our numbers are good. We hit 180, go around, hit 270 about, then back to 0. Now we have all our math done. Now we're just going to put it in a function like we did with the other one. Here's all our math. Let's make our function. Okay. All right, let's paste our math in. There we go. And then we want it to give us a value back, so let's set up a return statement. Okay. It's going to return us the angle that we calculate here. Now let's do that again up here. So var angle equals get rotation NPC player. So now this should give us the exact same thing from when we were walking in a circle around him a minute ago, or not. Okay, I missed a bracket. Where did I miss the bracket? Oh, I accidentally deleted the interact function bracket. There we go. All right, so there we go. Let's walk around him. We hit 90, hit 180, hit 270, then 360, back to 0. There we go. Now that we have this function, let's actually do something with it. The NPC API has a knockback method that you can use on entities. So this knockback method requires two inputs. It requires power and it requires direction. So let's just use this. We'll do it on the player. So player knockback, and then we'll just do 1 for power, and then we'll do 0 for the angle, just to show it off at the start. It's going to push me with 1 power in the 0 direction, and this is in the game world's coordinate frame. So 0 direction is that way. So no matter where I'm standing, it's going to push me that way, right? Push me that way. So as you can see, just giving a static number isn't necessarily useful for if you're trying to code a knockback function. What if we change it to the NPC's rotation? Right? Okay, so that's 0 when he was facing that way, and then it's a little better. Like as he turns this way, it's gonna face me. But if I go through him real quick, it's kind of pushing me in front of him. It's still not the best, right? But if we were to give it this angle that we get using our get player rotation, this is always going to push us away from the NPC, no matter where we are. Every single time, we're going to go straight away from the NPC. Even if we kind of go through him, it's going to push us away, which just feels much better in gameplay. That's our get player rotation function. That's the second function we're doing. Let's do the same thing we did to the other one. Let's just kind of hide it down here. Okay, let's get rid of this. Now let's move on to the third and final function, drawing a line of particles between two different points. How does that start? Obviously, it has to start with two different points. So let's define two different sets of coordinates to represent our 2 points. We're going to have the first point just be the NPC's location, and for the second point, we can just do the player's location. Okay, so there we go. We have x1, y1, z1, x2, y2, z2. So the location of the individual coordinates of the NPC and the individual coordinates of the player. Now we want to get the distance between the 2 points. So the distance, like how large is the distance between me and the NPC? We can start by just doing final minus initial. The change in the x value between us and the NPC is our x minus the NPC's x. Just to verify, let's have the NPC say this value. Right, so for here, it should be very small dx, right? It's close to 0. If we move farther away, to the negatives, gives us the difference. Over here, gives us the difference, right? Now we just want to do these for x, y, and z. So just change y, change z, change both these to y, change both these to z. There we go. So dx, dy, dz. Now we have the differences in each of the different coordinates. We have our difference in the x, difference in the y, difference in the z. How do we get the overall difference? In 3 dimensions, the Pythagorean theorem is the same as in 2 dimensions. So I'm sure you all know a squared plus b squared equals c squared. Well, we're going to do the same thing here. We're going to do the change in x squared plus the change in y squared plus the change in z squared is equal to the distance between us squared. So let's set that up really quick. Also in ECMA script, you can't do exponents like this. You'd have to represent that using math.pow a2, right? That's how you do exponents in ECMA script. Let's set that up for this distance here. And I want to write out math.pow a lot of times. So I'm just gonna be cheap and just do dx times dx. Don't worry, it's fine. Okay, so our distance is equal to dx squared plus dy squared plus dz squared, but we want it to be the square root, right? Because we just want the distance value. So we put 0.5 to get the square root. So this is going to give us the distance between us and the NPC. Okay, so it's going to say the distance between the 2 points we have. Okay, small distance. And then we're going to go farther. It's going to get bigger. There we go. Actually, let's make this a little bit nicer to look at. Okay, this is just going to round it to 1 decimal place. There we go. Now we have the distance between the 2 points. Now we need to determine how many particles we want to spawn in our particle line. The easiest way to do this is going to be by defining a resolution, which is going to stand for how many particles we want to spawn per block. Okay, and we'll do 3 particles per block. If we want 3 particles per block, and we have the distance in blocks between us, it might make sense that we can multiply these two values to get the total amount of particles we're going to spawn. Okay, so the distance times the resolution is going to give us the particle total. Now that we have the particle total, all we have to do is set up a for loop and spawn all those particles. Okay, so these will just be the coordinates where we're going to spawn the particles at. And then we'll set up our particle method down here. There's no need to get fancy with all the particle stuff, so we'll just do 0 for all the deltas and the velocity as well. Now we just need to get the position of each particle on each step of the for loop. So obviously we want the earliest particles to spawn at point 1, and we want the latest particles to spawn at point 2. So as I progresses, we want the particles to get closer and closer to the final point. At the start, obviously, it's just going to be at the start here. So x1, y1, z1, that seems obvious. Now we need to add an additional chunk of position to each of these for each iteration of the for loop. So because it's on each iteration of the for loop, we're just going to add I to each of them. Now, these dx, dy, and dz, that represents the overall amount of distance that needs to be covered between point 1 and point 2. We can use this and the ratio between I, our current loop variable, and the particle total to get us the amount of distance that we need to cover each loop iteration. So it'll be dx times I, right, times I divided by the particle total. So there, so the overall distance we need to cover times the ratio of the current step of the distance and the total amount of particles that need to be covered at the maximum distance. So let's just set these up for all 3. dy, dz. So dx, dy, dz. Let's see, I think everything's named right. I think we're good to give it a go. There we go. Spawns a line of particles between us. Now because my y is considered my feet and his y is considered his feet, it spawns kind of low. So if we add 1 to each of these, it should look a lot nicer. There we go. If I jump up, my y is considered higher, so it draws the particle line higher. Just like the last 2 times, now that we have the math done, let's put it into a function. Okay, so what are we going to need as our inputs? It's just going to be our 2 points. Okay, and then we should probably include our resolution as an input. So we have our 2 points and then the resolution. Let's copy all the math down. So here we go. All right, that's all we need. So we're going to give these as inputs. Okay, here's the math. We don't really need the comma anymore. And because the resolution is a function input right now, we don't need to define it anymore, but we do need to change the capitalization there. Okay, so now if we call this function up here, we have the names are the same, so we don't really need to change those. But we do need to give it a resolution. Let's just do 3 again. Okay, we got an error. What's the error? NPC is not defined. Ah, that's right. So we have the NPC down here spawning the particles. We need to give that as an input as well. Okay, change this to entity, and then pass this an entity, which we'll use. We could use NPC or player here because either of them are entities. Okay, you're erroring again. Distance is not defined. Oh, that's right. So we're having the NPC say the distance, but the distance, we're handling that down here in this function now. The interact function no longer knows what it is, but that's fine because we don't need it anymore. So there we go. Now we have the make particle line function, drawing particle lines in function form here. Now, what if we wanted the line to progress slowly, or have a time delay at least? For that, we're going to use a multi-thread block. If you're on my Discord server, you might have seen a message about the multi-thread block. I'm going to go over it very briefly here, and then we'll just implement it with the particle function, and you can just treat it as a black box. So this is a multi-thread. This defines the start of it. This defines the end of it. What this is good for is it allows you to use the sleep function. Thread sleep. Now, this number is in milliseconds, so whenever thread.sleep is reached, the code will wait that many milliseconds before running again. Now, it's very, very important that you never use thread sleep outside of a multi-thread. Otherwise, that's going to actually sleep your whole game and provide an effect that's very similar to server lag, which you don't want that. Just to show how this works, we're just going to use 2 say lines here. We have say 1 here, we'll do say 2 here, and then we'll return statement here, so that just stops the code here. So we're just showing off the multi-thread right now. So now the NPC say 1. It's going to have the thread wait a second, and then it's going to have the NPC say 2. There we go. So using this, we can add a delay to our particle line function. So we have the start of the thread here. Let's move the end of the thread down to the end of the function. And we want the sleeping to be while the particles are being drawn, so inside the for loop here. Let's make it a variable here that we can add as an input, so sleep time. And then add that as input. Okay, so the sleep time is in milliseconds, so it's very fast. So if we do something like 20 milliseconds, that's still going to make the particles move quickly. There we go, we see the particles progress at a rate of 1 particle every 20 milliseconds. If we want the line to move slowly, just do 200. There we go, see the line's moving slow now. And say we still wanted the line to show up instantly. If we did 0, it's going to do thread sleep 0, which isn't going to make it sleep at all. And the line's still going to show up instantly. So there we go. Those are our 3 functions. We have make particle line for making a line of particles. We have get player rotation for getting a rotation vector in the game world space between 2 entities. Doesn't necessarily have to be an NPC and a player, it could be any 2 entities. And then we have our front vectors function for getting us points in 3D spherical space and giving us the components needed to reach those points in the Minecraft XYZ Cartesian space. That's all I wanted to go over. Hopefully you were able to follow the math. I know it was a lot of math. Hopefully these functions help you guys out. And yeah, that's all. See ya.